You're standing under a dark American sky, maybe somewhere in Arizona's high desert, or out in the fields of Kansas, or on a quiet beach along the coast of California. The Milky Way stretches overhead like a river of frozen light. Every one of those faint points is a sun. Many of them have planets. Some of those planets might have oceans, mountains, maybe even life. And tomorrow morning NASA calls you with an impossible offer. A spacecraft is ready. Not science fiction, not a simulation. A real vehicle. You will board it, accelerate to the fastest speed humanity can realistically achieve, and travel for the rest of your natural life. 60 years in deep space. No turning back. No rescue mission. Just you, your ship, and the expanding darkness ahead. The question sounds simple, almost childlike. How far could you actually go? Could you reach another star? Could you stand beneath an alien sunrise? Or would you spend your entire lifetime crossing a distance so vast that, when you finally look back, the sun is still the brightest thing in your sky? Most people imagine that with enough determination and American engineering, we could push outward and touch the nearest stars. We put humans on the moon in the 1960s. We sent robots to Mars. We landed probes on comets and flew spacecraft past Pluto. We built the International Space Station. Companies like SpaceX are launching reusable rockets almost routinely. So surely, reaching another star in one lifetime can't be that far off. But the universe does not negotiate. It doesn't care about ambition, funding, or political will. It answers only to physics. The speed of light is not just a suggestion. Interstellar space is not just empty, it is staggeringly empty. And the mathematics of time, distance, and energy impose limits that are both awe-inspiring and devastating. Tonight, we're going to find out exactly what those limits are. We'll calculate how far you could travel in 60 years. We'll measure the distance to the nearest stars. We'll confront the brutal reality of propulsion, radiation, and cosmic dust at relativistic speeds. And by the end, you'll know which destinations are within reach, which are forever beyond the horizon, and what it would truly cost to leave the solar system behind. If you enjoy journeys like this, slow, immersive explorations of the cosmos that give your mind space to wander, take a moment to subscribe, like the video, and leave a comment. And here's your comment task for tonight. Tell us which part of the United States you're watching from. Are you in New York, Texas, Florida, Washington, somewhere in the Midwest? Let us know. It's incredible to imagine all of us scattered across one planet thinking about the same stars at the same time. Now take a slow breath. Let the scale begin to expand. The first thing we need to understand is just how far really is. On Earth, distance feels intuitive. You can drive across Los Angeles in an hour. You can fly from Chicago to Miami in a few hours. Even crossing the entire United States coast to coast takes less than a day in a commercial jet traveling around 500 miles per hour. Space does not work like that. The distances grow so quickly that our everyday language starts to fail. Let's begin close to home. The moon orbits Earth at an average distance of about 384,000 kilometers. At the speed of a commercial airliner, it would take nearly 3 weeks to get there. The Apollo missions, launched by NASA in the late 1960s and early 1970s, reached the moon in about 3 days because their Saturn V rockets pushed them to far higher speeds than any airplane could achieve. That alone required one of the most powerful launch vehicles ever built. Now move outward to Mars. At its closest approach, Mars is roughly 56 million kilometers from Earth. At its farthest, it's more than 400 million kilometers away. Even our fastest robotic missions take around 6 to 9 months to reach it. That's still inside our own solar system, still orbiting the same star, still practically in our backyard by cosmic standards. Next comes Jupiter, the largest planet in our solar system, orbiting at an average distance of about 778 million kilometers from the Sun. Missions like Juno took about 5 years to reach it. Saturn is nearly twice as far from the Sun as Jupiter. Uranus and Neptune lie even farther out, in a realm so distant that sunlight is hundreds of times dimmer than on Earth. When Voyager 2 flew past Neptune in 1989, it had already been traveling for 12 years. And then there's Pluto, once considered the 9th planet, now classified as a dwarf planet. When NASA launched the New Horizons spacecraft in 2006, it became the fastest spacecraft ever to leave Earth, reaching speeds of about 16 kilometers per second relative to the Sun. Even at that speed, it took nearly 10 years to reach Pluto. But Pluto is not the edge of the solar system. Beyond it lies the Kuiper Belt, a vast region of icy bodies. Beyond that lies the scattered disk. And farther still, possibly extending halfway to the nearest star, is the Oort cloud, a spherical shell of icy objects left over from the formation of the solar system. The outer edge of the Oort cloud may be 100,000 astronomical units from the Sun. 1 astronomical unit is the average distance between Earth and the Sun, about 150 million kilometers. Multiply that by 100,000 and you begin to sense the scale. Now let's talk about stars. The nearest star system to us is Alpha Centauri. It's actually a triple star system consisting of Alpha Centauri A, Alpha Centauri B, and Proxima Centauri. Proxima Centauri is the closest of the three, at a distance of about 4.24 light-years from Earth. A light-year is the distance light travels in 1 year, moving at about 300,000 kilometers per second. In 1 second, light can circle Earth more than 7 times. In 1 year, it travels about 946 trillion kilometers. Multiply that by 424, and you get roughly 40 trillion kilometers to Proxima Centauri. 40 trillion kilometers. To understand what that means for human lifetime, we need to examine speed. The fastest spacecraft humanity has ever launched, in terms of speed relative to the Sun, is the Parker Solar Probe, which will reach speeds of around under 90 kilometers per second at its closest approach to the Sun. That's astonishingly fast by human standards. A commercial jet flies at about 0.25 kilometers per second. The Parker Solar Probe moves nearly 800 times faster than a jetliner. But even at 190 kilometers per second, how long would it take to reach Proxima Centauri? If you do the math, it would take more than 6,000 years. And that's assuming you could maintain that top speed in the correct direction for the entire journey, which the Parker Solar Probe cannot. Realistically, with current chemical rocket technology, missions like Voyager 1 are traveling at about 17 kilometers per second relative to the Sun. At that speed, reaching Proxima Centauri would take around 75,000 years. 75,000 years. That's longer than recorded human history. When Voyager 1 was launched in 1977, disco was on the radio. Today, it has just barely entered interstellar space, crossing the heliopause in 2012, the boundary where the solar wind gives way to the interstellar medium. After nearly 50 years of travel, it is still less than 1 light day from Earth. 1 light day is the distance light travels in 24 hours. Proxima Centauri is more than 1/500 light days away. So if you boarded a spacecraft tomorrow and it used the same propulsion system as Voyager 1, you would not reach another star in 60 years. You would not even come close. You would spend your entire lifetime moving through the outer fringes of our solar system, perhaps approaching the inner Oort cloud if you were extraordinarily fortunate. The Sun would still dominate your sky, just another bright star among many, but brighter than the rest. This is the first heartbreaking limit imposed by physics. Chemical rockets, the kind that launched the space shuttle and power most missions today, are fundamentally inadequate for interstellar travel. They work by burning fuel and expelling hot gas at high speed. The problem is that to go faster, you need more fuel. But more fuel adds mass, and more mass requires even more fuel to accelerate. It's a vicious cycle described by the rocket equation, formulated by Konstantin Tsiolkovsky in the early 20th century. The equation shows that the amount of propellant required increases exponentially with the desired change in velocity. To reach a significant fraction of the speed of light using chemical propulsion would require more fuel than could ever be realistically carried. So if chemical rockets are not enough, what about nuclear propulsion? In the 1960s, NASA explored a program called NARVE, the nuclear engine for rocket vehicle application. Instead of burning chemical fuel, a nuclear thermal rocket would use a nuclear reactor to heat hydrogen propellant to extremely high temperatures, expelling it at higher speeds than chemical combustion allows. In theory, this could double or even triple the efficiency of traditional rockets. Speeds of perhaps 50 to 100 kilometers per second relative to the Sun might be achievable with advanced nuclear propulsion. That's a significant improvement. At 100 kilometers per second, you could cross the distance from Earth to Pluto in less than 2 years. You could explore the outer planets far more quickly. But when it comes to Proxima Centauri, even 100 kilometers per second would still require more than 12,000 years to arrive. A human lifetime remains a tiny blink compared to interstellar distances. This is where the conversation begins to shift from incremental improvements to radical ideas. If we truly want to reach another star within 60 years, we must start talking about fractions of the speed of light. Not kilometers per second, but tens of thousands of kilometers per second. 10% of light speed is about 30,000 kilometers per second. At that speed, Proxima Centauri could be reached in about 42 years from the perspective of Earth, ignoring acceleration and deceleration phases. Suddenly, a human lifetime begins to look almost sufficient. But achieving 10% of light speed is not just a technological challenge. It is an energy challenge on a scale that dwarfs anything humanity has ever attempted. The kinetic energy required to accelerate even a modest spacecraft to 0.1 c is enormous. The formula for kinetic energy in classical physics is 1/2 times mass times velocity squared. As velocity increases, energy increases with the square of velocity. Double the speed and you quadruple the energy required. At relativistic speeds, approaching a significant fraction of light speed, the energy requirements climb even more steeply due to Einstein's theory of special relativity. To accelerate a 1,000-ton spacecraft to 10% of light speed would require energy comparable to the total annual energy consumption of the entire human civilization, perhaps even more. And that's just for acceleration. You would also need energy to slow down when you reach your destination, unless you are content to fly past your target star at enormous speed, getting only a brief glimpse as you streak through the system. And then there are the hazards. Space is not completely empty. Even in interstellar space, there are stray atoms, dust particles, and microscopic grains of matter. At everyday speeds, these are harmless. At 10% of light speed, even a tiny grain of dust carries the kinetic energy of a high, explosive projectile. Your spacecraft would need shielding capable of absorbing countless high-energy impacts over decades. Radiation from cosmic rays would pose a serious threat to human health. Life support systems would need to operate flawlessly for generations of maintenance cycles. Every component would need redundancy upon redundancy. So when you ask, how far could you travel in one lifetime? The answer depends entirely on what speed you can achieve. With today's technology, you remain trapped within the solar system. With near-future nuclear propulsion, you might explore its outermost regions more efficiently, but the stars remain far beyond reach. Only by leaping to relativistic speeds, 10%, 20%, perhaps even higher, does interstellar travel within 60 years become conceivable. And even then, physics introduces another twist: time itself does not flow equally for everyone. As you approach the speed of light, time dilation becomes significant. According to Einstein's special relativity, a clock moving at high speed ticks more slowly relative to a stationary observer. If you travel at 90% of the speed of light, time aboard your spacecraft passes much more slowly than time on Earth. You might experience 60 years while centuries pass back home. This creates an impossible choice. Travel far and fast and you lose synchronization with the era you left behind. Stay slow enough to remain connected, and you never reach the stars. This is the cruel mathematics of interstellar ambition. Distance, speed, energy, and time are intertwined. You cannot change one without affecting the others. The universe sets the rules, and we must decide whether we are willing to pay the price. For now, as we end this first chapter of our journey, hold on to this image as a single human life, 60 years long, set against the backdrop of a galaxy 100,000 light-years across. Our Milky Way contains hundreds of billions of stars. Yet with today's rockets, even the nearest one is tens of thousands of years away. The dream of traveling through space in one lifetime is not impossible, but it demands speeds and energies that push us to the edge of known physics. We confronted the scale of the problem. We measured the distance to the nearest stars. We compared it to the speeds of our fastest probes. We felt, perhaps for the first time, the quiet weight of numbers like 40 trillion kilometers. Now, in this second chapter, we begin to redraw the map. Not the romantic map of science fiction where warp drives hum and galaxies shrink to manageable proportions, but a realistic map based on speeds we might plausibly achieve within the next century. If you were given 60 years aboard a spacecraft, your entire adult life spent moving outward, what would your reachable universe actually look like? Let's start with a clear assumption. You board your spacecraft at age 20. You remain alive and healthy until 80. That gives you 60 years of travel time. For simplicity, we'll assume you accelerate for part of the journey, cruise at top speed, and then decelerate so that you can actually stop when you arrive. Because arriving at a new star system at 10% of the speed of light without slowing down would be like trying to explore New York City by flying past it in a fighter jet at full throttle. You would see everything in seconds and then be gone forever. So your 60 years must include acceleration, cruising, and braking. That immediately reduces the maximum distance you can cover compared to a simple speed multiplied by time calculation. But even with that limitation, the numbers become astonishing once we move beyond chemical rockets. Imagine we somehow develop a propulsion system capable of reaching 10% of the speed of light, 0.1 c, about 30,000 kilometers per second. This is not possible with chemical rockets. It likely requires fusion propulsion, perhaps using reactions similar to those that power the sun, but controlled inside a spacecraft engine. Concepts like Project Daedalus, studied by the British Interplanetary Society in the 1970s, suggested that unmanned probes might reach around 0.1 c using fusion micro-explosions. Scaling that to a crewed vehicle is a different challenge, but let's remain optimistic. At 0.1 c, 1 light year takes 10 years to cross from the perspective of Earth, ignoring acceleration and deceleration. So in 60 years, you might think you could travel 6 light years, but because you need to speed up and slow down, the realistic range is smaller, perhaps 4 to 5 light years if you want to arrive safely and enter orbit around a new star. Now remember that Proxima Centauri is 4.24 light years away. At 0.1 c, with efficient acceleration and braking, reaching Proxima within a lifetime becomes just barely feasible. Alpha Centauri A and B are slightly farther, but still within about 4.37 light years. Suddenly, for the first time in human history, another star system enters the realm of the possible. Proxima Centauri is not just any star. It hosts at least one confirmed exoplanet, Proxima Centauri b, orbiting within the star's habitable zone. That means, in theory, liquid water could exist on its surface. The star itself is a red dwarf, smaller and cooler than our Sun, but red dwarfs are the most common type of star in the galaxy. If you could stand on Proxima b, assuming it has a solid surface, you might see Alpha Centauri A and B shining brightly in the sky, like twin suns in the distance. The idea that a human being born on Earth could live long enough to see that sky with their own eyes transforms interstellar travel from fantasy into a brutally difficult engineering problem. But Proxima Centauri is only the beginning. Within about 5 light years of Earth, there are only a handful of star systems. The solar neighborhood is surprisingly sparse. The next nearest stars beyond Alpha Centauri include Barnard's star at about 5.96 light years and Wolf 359 about 7.9 light years at 0.1 c. Barnard's star might be just out of reach if you insist on stopping upon arrival. Wolf 359 would likely remain unreachable within a 60-year lifespan unless you were willing to forego deceleration and simply perform a high-speed flyby. This reveals something important. Even at 10% of light speed, an almost unimaginable velocity compared to anything we have achieved, your reachable bubble of space remains tiny. Picture a sphere centered on the Sun with a radius of roughly 5 light years. Inside that sphere are perhaps a dozen stars. Outside it are hundreds of billions more, permanently inaccessible within your lifetime. So what if we push further? What if we achieve 0.2 c, 20% of the speed of light? At 0.2 c, you cross 1 light year in 5 years of Earth time. In 60 years, ignoring acceleration and braking, that's 12 light years. Realistically, with acceleration and deceleration phases, perhaps 8 to 10 light years become reachable. That expands your sphere dramatically. Suddenly, dozens of star systems fall within range. Within 10 light years of Earth, there are roughly a few dozen known stars and brown dwarfs. Some host exoplanets. Some may host rocky worlds in their habitable zones. With 0.2 c propulsion, you are no longer limited to a single target like Proxima Centauri. You could choose from multiple destinations. You could aim for a system with confirmed Earth-sized planets. You could even consider a mission profile that visits more than one star, if your life support systems and energy reserves allow. But reaching 0.2 c is not just twice hard as reaching 0.1 c. The energy required increases with the square of velocity. Doubling your speed from 0.1 c to 0.2 c requires 4 times as much kinetic energy, and that's before accounting for inefficiencies in propulsion. Fusion might get us to 0.1 c in optimistic scenarios. To push toward 0.2 c, we may need even more advanced systems. Perhaps antimatter propulsion, where matter and antimatter annihilate to release energy according to Einstein's famous equation, E equals mc squared. Antimatter is the most energy-dense fuel we know of. When a gram of antimatter meets a gram of normal matter, the energy released is equivalent to tens of kilotons of TNT. In principle, antimatter propulsion could push spacecraft to relativistic speeds. In practice, we can barely produce and store tiny fractions of a gram in particle accelerators, and doing so costs astronomical amounts of money. Containing antimatter safely for decades aboard a spacecraft introduces engineering challenges that border on science fiction. And then we encounter relativity in a more profound way. At 0.1 c, time dilation is small but measurable. At 0.2 c, it becomes slightly more noticeable. But as you approach higher fractions of light speed, 0.5 c, 0.8 c, 0.9 c, time aboard the spacecraft begins to slow dramatically relative to Earth. If you could somehow reach 0.9 c, 90% of the speed of light, the relativistic effects become impossible to ignore. The time dilation factor, known as gamma in special relativity, increases as velocity approaches light speed. At 0.9 c, gamma is about 2.3. That means if you experience 60 years aboard your ship, roughly 138 years pass on Earth. Your friends, your siblings, your entire generation would be gone by the time you arrived. The United States you left behind would be unrecognizable. Languages shift, borders change. Technology transforms. You would not just be traveling through space, you would be traveling into the future. Push to 0.99 c and gamma rises to about 7. If you experience 60 years, more than 4 centuries would pass on Earth. Entire eras of history would unfold while you cruised between the stars. You would arrive at your destination as a relic of the past, a human being from a civilization long vanished. This is the second heartbreaking limit imposed by physics. The faster you go, the farther you can travel within your own lifetime. But the faster you go, the more you detach from the timeline of the world you left behind. There is no way to cheat this. You cannot both reach distant stars quickly and remain synchronized with Earth's history. The universe forces you to choose. Now let's consider another constraint: acceleration. Humans are fragile compared to machines. Sustained high acceleration would be deadly. Fighter pilots can endure several Gs, several times Earth's gravity, for short periods. But for a long-duration interstellar voyage, you might aim for a comfortable acceleration of 1 g, similar to Earth's gravity, so that passengers can walk normally inside the spacecraft. If you accelerated at 1 g continuously, you would reach extraordinary speeds surprisingly quickly. In fact, constant 1 g acceleration for about 1 year would bring you close to light speed, at least in theory, ignoring fuel constraints. But maintaining 1 g acceleration for a year requires colossal amounts of energy and propellant. The mass of fuel required becomes the central obstacle. Some theoretical concepts propose light sails, like those envisioned by breakthrough starshot. Instead of carrying all your fuel with you, a powerful laser array in the solar system would push a lightweight sail attached to a tiny spacecraft, accelerating it to perhaps 0.2 c over minutes. The challenge is that such probes would be extremely small, gram-scale payloads, not crude vessels with life support systems. They could reach Alpha Centauri in about 20 years, but they would not slow down. They would streak through the system in hours, transmitting data back to Earth before disappearing into the dark. For a human crew, deceleration is non-negotiable. You cannot step out onto an alien world if you are moving at a fifth of the speed of light relative to it. That means either carrying fuel for braking, using magnetic sails to interact with the interstellar medium, or somehow leveraging the stellar wind of your destination star to slow down. Each method adds complexity and mass is the enemy of speed. The heavier your spacecraft, the more energy you need. The more shielding you add to protect against radiation and micrometeorites, the heavier you become. The more life support redundancy you build in, the more mass you carry. It becomes a delicate balance between safety and feasibility. Strip the ship down to the bare minimum, and you risk catastrophic failure decades from Earth. Over-engineer it, and you may never reach the required velocity. Within this web of constraints, we can sketch a realistic scenario. With advanced fusion propulsion achieving around 0.1 c to 0.1 c, a small number of nearby star systems, perhaps those within 5 to 7 light years, become reachable within 60 years, including deceleration. This likely includes Proxima Centauri and possibly Barnard's star if you push the limits. With even more advanced systems approaching 0.2 c, the reachable sphere expands to perhaps 10 light years, encompassing dozens of stars. But even at that level, you are exploring only a tiny bubble in a galaxy 100,000 light years across. If you draw a sphere 10 light years in radius and compare it to the full disk of the Milky Way, it is like exploring a single grain of sand on an entire continent. The overwhelming majority of the galaxy remains forever beyond the reach of a single human lifetime, unless new physics, warp drives, wormholes, space-time manipulation, turn out to be possible. And as of now, those remain purely theoretical, with no experimental evidence that they can be engineered. So how far could you actually travel in one lifetime? With today's rockets, you would barely escape the sun's gravitational domain. With near-future nuclear propulsion, you would explore the outer solar system more efficiently, but still never reach another star. With optimistic fusion technology, you might reach one or two neighboring systems. With extreme relativistic travel approaching light speed, you could cross dozens of light years, but at the cost of leaving your entire era behind. The map of reachable space is not infinite. It is a fragile, glowing bubble surrounding the sun. Inside it lie a few dozen stars, some with planets that may resemble Earth in size and temperature. Outside it lies the vast majority of the Milky Way, unreachable within a single life bounded by biology. And yet, that small bubble is not empty. It contains possibilities. It contains new suns, new worlds, new skies no human has ever seen. In cosmic terms, it is tiny. In human terms, it is everything.